All right, welcome back to the deep dive. Today we're going up and away. We're diving into the world of
Oh,
helicopters.
this is going to be fun. Always love these machines. Pure engineering magic.
Right. I mean, defying gravity, it's just not cool. And today we're going to get into the nitty-gritty. How do these things actually work? We've got a whole chapter here breaking down the core components, sections, and systems that make these things tick.
Yeah, it's pretty amazing how much goes into making a helicopter fly. And there's a surprising amount of variation out there.
Tons of variety, different sizes, different purposes, but under the hood, they share a lot of the same fundamental building blocks, right?
Absolutely. No matter if it's a little trainer or a massive heavy lifter, you've got the same basic ingredients.
So what are we looking at here? Our source breaks it down into 7 key components. Let me see if I can remember them all. We've got the airframe, the fuselage, landing gear, of course. Then there's the power plant.
The heart of the beast.
Exactly. Then the transmission system to get that power where it needs to go. And of course, the main rotor system, that's the star of the show,
The
right?
big spinny thing on top. Can't forget that.
Of course, of course. And last but not least, the tail rotor system, keeping everything pointed in the right direction.
Yeah, without that, we'd just be spinning in circles. Not very useful for getting anywhere.
So let's start with the basics. The airframe. What exactly are we talking about here?
Think of it as the skeleton, the framework that holds everything together. It has to be strong, light, and able to handle all those stresses and strains of flight.
And they can use all sorts of materials to build these things, right?
Absolutely. You see metal, wood, composites, sometimes even a mix of different materials depending on the design and the job it needs to do.
Composites. Those are, what are those again?
So imagine layers of like fabric or fibers impregnated with a special kind of resin. You stack them up, cure them under heat and pressure, and bam, you get these super strong, super light panels. They're pretty amazing, really.
And then you mentioned the more traditional materials like metal.
Yeah, a lot of the substructures are made from aluminum. Tubular forms, sheet metal, very versatile. But in those areas that really take a beating, high stress, high heat, they might use stainless steel or even titanium.
So designing a helicopter airframe, it sounds like a real balancing act.
Oh, it definitely is. It's all about juggling engineering principles with aerodynamics, material science, and how efficiently you can build the thing. You got to make it strong, light, reliable, and affordable.
Not an easy task.
Huh.
Okay, so moving on to the fuselage, I guess that's basically the cabin area, right?
Yeah, that's the main body of the helicopter. The outer shell houses the cabin where you have the crew, passengers, any cargo. And the layout of that cabin can be pretty different depending on the role of the helicopter.
I'm guessing a military transport helicopter looks a lot different inside than, say, a sightseeing tour helicopter.
Oh, absolutely. And even the pilot seating can vary. Usually the pilot's on the right, but there are some helicopters where they're in the center or even on the left.
Hmm, interesting. So besides the people and cargo, the fuselage houses a lot of the, I guess, the operational guts of the helicopter.
Yeah, it's kind of like the central nervous system. You've got the engine, the transmission, all the avionics for navigation and communication, flight controls, the power plant. It's all packed in there.
All right, well, let's move on up to the part that really makes a helicopter a helicopter. The main rotor system. This is what gives it the lift to get off the ground, right?
Exactly. And it's made up of a few key parts. You've got the mast, which is that big hollow shaft that runs up from the transmission. Then you've got the hub where the blades attach. And of course, the rotor blades themselves, those are what do the actual lifting.
And the way these blades are attached and how they move, that's how we get the different types of main rotor systems, right?
Yeah.
I've heard terms like semi-rigid, rigid, and fully articulated.
That's right. Let's start with the semi-rigid system. This one typically uses two blades that are rigidly attached to the hub, but the hub itself can tilt back and forth.
So the blades are fixed, but the whole hub can move.
Yeah, thanks to a special hinge called a teetering hinge or flapping hinge. So as the blades rotate, they can flap up and down together, but only as a unit. One goes up, the other goes down.
Hmm, like a seesaw. And what about those lead lag forces, the blades moving forward and backward as they spin?
In a semi-rigid system, there's no separate hinge for that. The blades actually absorb those forces by bending. Pretty cool, huh? And of course, you still have feathering. That's where the pitch angle of the blades changes to control lift and direction.
Right, right. And within the semi-rigid category, there's this thing called an underslung rotor. What's that all about?
Underslung, yeah. It's basically what it sounds like. The whole rotor system hangs a bit lower than usual. The center of gravity is actually below the point where it attaches to the mast.
So it's like the rotor's hanging from the mast rather than sitting on top of it. Why would they do that?
Well, it helps to line up the blade center of mass with that flapping hinge so as they go up and down, they stay balanced. This reduces a lot of the forces that would otherwise try to change the rotor's speed as it spins.
So smoother, more stable rotation.
Exactly. And it means they don't need to make the blade roots as stiff, which saves weight. It also helps manage those lead lag forces, and any leftover stresses just get soaked up by the blade's bending.
Okay, makes sense. Now, our source mentions something called mast bumping. Sounds a bit, concerning.
Yeah, this is a potential issue with semi-rigid rotors. You see, because of that teetering hinge, there needs to be a limit on how far the blades can flap down. If they go too far, you can get this violent contact between a part called the static stop and the mast itself.
Ouch. That doesn't sound good. What can cause that to happen?
Several things. High forward speeds, low rotor RPM, high density altitudes being really heavy, turbulence. They can all increase the flapping. Even things like side slips or flying slow with the helicopter's center of gravity in a weird position can make it happen.
And normally, how much flapping are we talking about?
In smooth, level flight, it's pretty minimal, maybe around 2 degrees or so. But when those conditions I mentioned come into play, the flapping can get much more extreme.
Definitely something to avoid. Okay, let's switch gears and talk about the rigid rotor system. That sounds like it might be a bit less prone to all that flapping.
It is. In a rigid rotor system, the blade roots are bolted directly to the hub. No hinges for flapping or lead lag. All that movement is absorbed by the blade's bending.
So the blades are doing all the work, both lifting and flexing.
Exactly. Now, this means the blades have to be designed to handle those extra stresses, so the structure can be a bit more complex. But on the plus side, it's mechanically simpler, fewer moving parts.
And they behave like fully articulated systems in terms of the aerodynamics, right?
Yeah, pretty much. You get similar airflow patterns and control responses. And with all the advances in materials science and computer modeling, rigid rotors are becoming more and more common. They combine some of the best features of both semi-rigid and fully articulated systems.
What would you say are the biggest advantages of the rigid rotor design?
Well, they tend to be very responsive to control inputs. No slop in the hinges. And they're not really prone to mast bumping because the hub is bolted solid to the mast.
Makes sense. Anything else?
Yeah, usually the rotor and fuselage move more as a single unit, which helps with stability. The hub itself tends to be lighter and have less drag, and you often need smaller control inputs from the pilot to achieve the same effect.
Less work for the pilot. I like it. Any downsides?
Well, the ride can be a bit rougher, especially in turbulence. Because there aren't any hinges to soak up those bumps, you feel more of the vibrations in the cabin.
Okay, so it's a trade-off. A smoother ride versus better responsiveness and simpler mechanics. Now, you mentioned bearingless rotors earlier. What are those all about?
These are pretty cool. They're kind of like a hybrid. They have the aerodynamic benefits of a fully articulated system, but instead of traditional bearings and hinges, they rely on the flexibility of the blades and the hub structure to allow for movement.
So the blades themselves are the hinges, in a way.
Exactly. And they mostly use advanced composite materials, which can be designed to flex and bend in very specific ways. The key difference from a rigid system is that there's no separate feathering bearing. The cuff, where the blade attaches to the hub, is designed to twist when the pilot changes the blade pitch.
It's fascinating how much material science plays into all this. Okay, let's move on to the fully articulated system. This one sounds like it gives each blade the most freedom to move around.
It does. Each blade can lead or lag, which means it can move forward or backward in the plane of rotation. They can flap up and down on a hinge near the root, and they can feather, changing their pitch angle to control lift.
So each blade is kind of dancing around on its own little hinges.
In a way, yes. And this is what allows for fine control of the helicopter's movements. The pilot uses the collective control to change the pitch angle of all the blades at the same time, increasing or decreasing lift for vertical movement. And the cyclic control changes the pitch of each blade individually as it rotates, creating tilting forces for forward, backward, and sideways movement.
So it's like a synchronized dance, but each blade is following its own choreography based on those control inputs.
Exactly. And as each blade flaps up or down, it causes its center of gravity to shift a bit. This affects its momentum and makes it want to speed up or slow down in rotation, which is why we need that lead lag hinge to let it adjust. It's like an ice skater pulling their arms in to spin faster.
Okay, I can picture that. So as the blade encounters more lift, it flaps up, speeds up slightly in rotation. Then as the lift decreases, it flaps down and slows down. This is all happening constantly as the blades spin.
All the time. It's a continuous cycle, and the lead lag dampers help smooth out those movements. And because the whole rotor system is spinning, it also acts like a gyroscope. This means the pilot's control inputs actually have their biggest effect about 90 degrees later in the rotation. But don't worry, the engineers who design these things take that into account so the helicopter responds the way you'd expect.
That's pretty wild. So when you push the cyclic forward, the helicopter starts tilting forward a quarter turn later because of that gyroscopic effect.
Yeah.
Amazing.
Yep, physics at work. And the technology of those hinges has evolved too. Older designs used metal bearings, which could be a pain to maintain. Now they're using elastomeric bearings made from layers of rubber and steel.
So those are more durable and easier to take care of.
Exactly. They can handle movement in two directions, they're self-lubricating, and they wear down gradually so you can spot problems before they become catastrophic. Now, what about those helicopters with two sets of main rotors, the ones with the tandem rotors or coaxial rotors? How do those work?
Yeah, those are pretty unusual looking.
They are. So tandem rotors, you have two big rotor assemblies, one at the front, one at the back, spinning in opposite directions. This kind of rotation cancels out the torque that a single main rotor would produce.
So no need for a tail rotor.
Exactly. Plus, you get more lifting power because you have two sets of blades, and you can use shorter blades, which makes the helicopter more maneuverable.
And coaxial rotors, those are the ones stacked on top of each other, right?
Yep. Two rotors, same mast, spinning in opposite directions. This also eliminates the need for a tail rotor and helps balance out the lift forces more evenly. The downside is that they're mechanically more complex.
And then there's the intermeshing rotors, where the blades actually weave between each other.
Those are pretty wild. Two rotors, slightly angled masts, the blades intermeshing without hitting each other. Again, no tail rotor needed, more power to lift. But the slight angle means neither rotor is lifting straight up, so you lose a bit of efficiency there.
It's amazing the different ways they've figured out to make these things fly. Okay, so we've talked about how the main rotor creates lift. But how do the pilot's control inputs actually translate into all that complex blade movement? That's where the swash plate comes in, right?
The swash plate is like the translator between the pilot and the rotors. It takes the stationary control inputs from the cyclic and collective sticks and turns them into rotating inputs for the blades.
Okay, walk me through it.
So you have two main parts: a stationary swash plate mounted around the mast, and a rotating swash plate that sits on top of it. The stationary one is connected to the cyclic and collective controls, and it can tilt and move up and down. The rotating one is connected to the mast and follows the movements of the stationary one.
So when the pilot moves the controls, the stationary swash plate tilts or moves up and down, and the rotating one follows along.
Exactly, and the rotating swash plate is connected to the pitch horns on each blade, so as it moves, it changes the pitch angle of the blades. This creates the changes in lift that make the helicopter move in different directions.
Brilliant. Now, what about the freewheeling unit? What does that do?
This is a really important safety feature. It basically disconnects the engine from the main rotor if the engine fails.
So if the engine quits, the rotor blades can keep spinning.
Exactly. That's what allows for auto rotation. The most common type is a sprag clutch, and it sits between the engine and the transmission. In normal operation, it locks the engine and rotor together. But if the engine slows down too much, the clutch releases, letting the rotor spin freely.
I'm guessing that's a pretty important thing to have in a helicopter. Now, with all the spinning going on, we need a way to keep things from, well, spinning out of control. That's where the anti-torque system comes in, right?
Right. A single main rotor creates a lot of torque, which would make the helicopter spin in the opposite direction if it wasn't counteracted. The most common solution is the tail rotor.
The little propeller at the back.
That's the one. It produces thrust sideways to counteract the main rotor's torque. The pilot controls it with the pedals, and it's usually driven by the transmission, so it keeps working even if the engine fails.
And there are other ways to do this too, right? The fenestron and the notar system.
Those are some interesting alternatives. The fenestron is basically a ducted fan built into the tail. It's safer because the blades are enclosed, and it's quieter too.
And notar stands for no tail rotor, right? So how does that work?
It's pretty ingenious. It uses a fan inside the tail boom to create a low-pressure area. This interacts with the downwash from the main rotor, creating a sideways force that cancels out most of the torque. Then there's a small jet thruster at the end of the tail boom for fine control.
So it's basically using the airflow itself to control the helicopter's direction. Amazing. And all this anti-torque stuff needs a way to get power from the transmission to the tail, right?
Right. There's usually a long drive shaft running back to the tail, or sometimes a series of shorter shafts with flexible coupling so the tail can bend a bit. And there's a gearbox at the tail to change the direction of rotation and adjust the speed for the tail rotor.
Okay, that covers the rotors and how we control them. Now let's talk about what makes them spin in the first place.
Hmm.
The power plant or the engines. We see both reciprocating engines and turbine engines in helicopters, right?
Yeah. Reciprocating engines, those are basically your classic piston engines. They're simpler and cheaper to operate, so you often see them in smaller helicopters, especially for training. For a deep dive into how those work, you can check out the FAA's Pilot's Handbook of Aeronautical Knowledge.
Always a good resource. And turbine engines are more powerful, right?
Much more powerful. They're the go-to for anything bigger than a small trainer. They're incredibly powerful for their size, but they're more complex and expensive to maintain.
And in helicopters, the exhaust from the turbine doesn't really contribute to thrust like it does in airplanes, right?
Nope, most of the time it's just exhaust. The main job of the engine is to spin the rotors. In fact, a lot of the air going into the engine is actually used to cool it down.
So it's a hot job spinning those rotors. What are the main parts of a turbine engine?
You've got the compressor, the combustion chamber, the turbine section, and the accessory gearbox. The compressor sucks in air, filters it, and squeezes it down to a much higher pressure. It's important to keep those filters clean, especially in dusty environments.
Yeah, a clogged filter can really mess things up. So what happens to that compressed air?
It goes into the combustion chamber, where fuel is injected and burned continuously. The expanding hot gases spin the turbine wheels, which power the compressor and the accessory gearbox. And the exhaust, well, that just goes out the back.
And there are two main types of compressors, right? Axial and centrifugal.
Yep. An axial compressor uses rows of spinning blades to gradually increase the air pressure. A centrifugal compressor uses a spinning impeller to fling the air outwards, and then the diffuser slows it down and increases its pressure.
So two different ways to squeeze the air, and sometimes things can go wrong with the compressor. What's that thing called? Compressor stall.
Yeah, that's when the airflow over the compressor blades gets disrupted. You can get vibrations, loss of power, and the engine might start running hotter.
And most turbine engines have a bleed air system to help deal with that.
Right. It can vent off some of that compressed air to try and reestablish smooth airflow. So after the compressor, we have the combustion chamber, which is where the magic happens. The fuel mixes with the compressed air and burns. Most turbine engines don't need an igniter once they're running. The flame just keeps going. But if the fuel or air supply gets cut off, you can get a flame out. Some helicopters have automatic relight systems, though, which is pretty handy.
And then the hot gases from the combustion chamber spin the turbine, which has two main parts, right?
The gas producer turbine, or N1, and the power turbine, or N2. In most helicopter engines, these are on separate shafts, which is called a free turbine design. The N1 spins the compressor and the engine accessories, and the N2 drives the rotors through the accessory gearbox.
Okay, so it's a two-step process. The hot gas spins the first turbine, which powers the engine, and then the second turbine, which powers the rotors.
Exactly. And the accessory gearbox is like the central hub for all that power. It takes the output from the N2 turbine and distributes it to the main rotor, the tail rotor, and all the other things that need power, like generators and air conditioning.
Makes sense. So we've got the engine generating all this power. Now we need to get it to the rotors. That's the job of the transmission system, right?
Right. It's the link between the engine and the rotors. It includes the main rotor transmission, the tail rotor drive system, and that freewheeling unit we talked about earlier. It also often has a clutch, so you can start the engine without spinning the rotors right away.
And the transmission is pretty important for keeping everything lubricated too, right?
Oh, absolutely. It usually has its own oil supply, and there's often a sight gauge to check the level. Many transmissions also have chip detectors, which are like little magnets that catch any tiny metal fragments that might be floating around in the oil.
So that's a way to catch potential problems early.
Exactly. If the chip detector finds too much metal, it'll trigger a warning light. And some even have a burn-off feature to try and clear out any harmless particles. But if that light stays on, you know something's wrong, and you need to take action.
Okay, that makes sense. And the main rotor transmission, it's got a pretty big job, right? Taking that high engine speed and slowing it way down for the rotors.
Yeah, that's right. The exact reduction ratio depends on the helicopter, but it might be something like 6-to-1 or even 9-to-1. And pilots have these dual tachometers in the cockpit to monitor both the engine RPM and the rotor RPM.
So they can see if things are spinning at the right speeds.
Exactly. Keeping that rotor RPM within limits is crucial, especially if you have an engine failure and need to auto-rotate. And if the rotor tachometer fails, you can sometimes use the engine tachometer to estimate the rotor speed because of that fixed ratio through the freewheeling unit. But there have been cases where Pilots, thinking the rotor had failed, initiated an auto rotation when the engine was actually fine. It's important to interpret those instruments correctly.
Right, right. And sometimes the transmission also has to change the direction of the power flow, right? Like
Right.
if the engine is mounted horizontally.
Exactly. If the engine's output shaft is horizontal, the transmission needs to turn that 90 degrees to drive the vertical rotor mast. It's a pretty ingenious piece of engineering.
And you mentioned a clutch earlier. How is that different in a helicopter compared to a car?
Well, in a car, the clutch is mostly there so you can change gears. But in a helicopter, it's mainly used to disconnect the engine from the rotors when you're starting up.
Why is that?
Because those rotors are heavy. It takes a lot more power to get them spinning than it does to start a car engine. So the clutch lets you start the engine and get it running smoothly before engaging the rotors.
And helicopters with free turbine engines, they don't always need a separate clutch, right?
Right. The air coupling between the N1 and N2 turbines acts like a clutch. But for reciprocating engines and fixed turbine engines, you do need a clutch. There are a couple of common types: the idler clutch, which is sometimes a belt drive system, and the centrifugal clutch.
So the idler clutch uses belts to connect the engine and transmission.
Yeah, and you tighten those belts to engage the rotors. It's simple, and it isolates vibrations well,
Mhm.
but you have to be careful with the throttle because it's easy to overspeed the engine if you're not paying attention.
And centrifugal clutch?
That one uses weighted shoes that fly outward as the engine speed increases, engaging the rotors gradually. It's a pretty smooth and reliable system.
Okay, so we've got the power from the engine to the rotors. Now we need to talk about fuel systems.
Right. There are two main parts to a helicopter's fuel system: the fuel supply system and the engine fuel control system. The fuel supply system is all about getting the fuel from the tanks to the engine. It includes the tanks, fuel gauges, shut-off valve, filter, lines, maybe a primer, and pumps.
And those fuel tanks, they're positioned carefully, right?
Absolutely. You want them as close to the helicopter's center of gravity as possible so the balance doesn't change too much as you use up fuel. And each tank has a drain for water and sediment, a vent to prevent vacuum, and an overflow drain in case it gets too full.
Good to know. So the fuel gets from the tank to the engine through those lines, and there's a shut-off valve for emergencies. And what about those pumps you mentioned?
Most helicopters have both an electric pump and an engine-driven pump. The electric one is a backup and can provide positive pressure if needed. The engine-driven pump is the main workhorse, pumping fuel at high pressure to the engine.
And there's a fuel filter to keep things clean, right?
Absolutely crucial. It catches any dirt or water that might be in the fuel before it reaches the engine. And then there's the engine fuel control system.
That's what figures out how much fuel to give the engine.
Exactly. It has to work with the air induction system to ensure the right fuel-air mix for efficient combustion. It's a pretty complex system, and the details vary depending on the type of engine.
Okay, and you mentioned something about carburetor ice earlier. That's a problem for reciprocating engines, right?
Right. It happens when moisture in the air freezes inside the carburetor. It can block the airflow and cause the engine to lose power or even quit. It's particularly risky when you're descending with reduced power.
So what can pilots do about it?
They need to monitor the carburetor air temperature gauge and use carburetor heat if needed. It basically routes warm air from the engine to melt the ice. Turbine engines don't have this problem because they use fuel injection.
Okay, so fuel injection is better in that regard.
Yeah, and it has other benefits too. It's more efficient, and it delivers the fuel directly to the cylinders or combustion chambers, so you get better performance.
Now, let's move on to the electrical system. I guess with all the modern avionics and gadgets and helicopters, electricity is pretty important.
Absolutely. You can still fly a helicopter without electrical power in an emergency, but it's certainly not ideal. Most helicopter electrical systems run on either 14 or 28 volts DC.
And they use alternators or generators to produce that power, right?
Exactly. Smaller helicopters often use engine-driven alternators, which are lighter and more efficient than old-style generators. Turbine engines typically have a starter generator, which does double duty. It acts as a starter motor to get the engine going, and then it switches to generator mode once the engine's running.
So it's like a two-in-one deal. And there's a voltage regulator to keep the voltage stable, right?
Yep. And you've got bus bars to distribute the power, a battery for starting and backup, and an ammeter to monitor the current flow.
So the ammeter tells you if the battery's charging or discharging.
Exactly. And it can also indicate if there's an electrical problem somewhere. Then you have switches for the various components and circuit breakers or fuses to protect the system from overloads.
Okay, so it's a pretty complex network of wires and components. Now let's talk about hydraulics. I know a lot of helicopters use hydraulics for the flight controls, right?
Yeah, most of the larger ones do. It's because those controls can require a lot of force to move, especially at higher speeds. The hydraulic system helps boost the pilot's input, making it much easier to control the helicopter.
So it's like power steering for the helicopter.
In a way, yes. A typical system has actuators on each control, a pump driven by the transmission, and a reservoir for the hydraulic fluid. Some helicopters also have accumulators to maintain pressure.
And there's a switch in the cockpit to turn the hydraulics on and off.
Right. The ARN position actually de-energizes the system, opening a valve and letting fluid flow to the actuators. The off position closes the valve, trapping the fluid. It's a fail-safe system, so even if you lose electrical power, you still have some control.
And if the hydraulics completely fail, can you still fly the helicopter?
You can, but it takes a lot more muscle. The controls will be very heavy. That's why some helicopters have multiple hydraulic systems for redundancy. And those accumulators I mentioned can provide a bit of backup pressure in case the pump fails, giving you some time to land safely.
Okay, that's reassuring. Now, what about stability augmentation systems, or SAS? I know those can help make the helicopter easier to fly.
Definitely. SAS helps smooth out the ride and reduce the pilot's workload, especially in hover. It can do things like dampen out oscillations and keep the helicopter stable in gusty winds.
So it's like having a co-pilot who's constantly making tiny adjustments.
Kind of, yeah. There are a few different types of SAS. A simple one is force trim, which helps hold the cyclic stick in position, reducing the force the pilot needs to apply. It can be really helpful for pilots transitioning from airplanes.
So it makes the controls feel more familiar.
Exactly. Then you have active augmentation systems, which use sensors to detect things like wind gusts and turbulence. They send signals to actuators that move the controls to counteract those disturbances.
So it's like having a computer constantly monitoring the flight and making tiny corrections to keep things smooth.
Exactly. And these systems can get pretty sophisticated. Some can stabilize the helicopter in all three axes, pitch, roll, and yaw, and they can even adjust the power and trim settings.
And the pilot can always override them if needed.
Absolutely. It's important to have that ultimate control. And then we have autopilots, which take things to another level.
So an autopilot can actually fly the helicopter for you.
Up to a point, yes. It depends on the type of system, but it can do things like hold altitude, maintain heading, even fly instrument approaches.
Wow, that's pretty advanced.
It is. Some autopilots can even fly a complete approach to a hover without any input from the pilot after the initial setup. They use actuators connected to the controls and a computer that processes data from the instruments and navigation equipment to figure out what to do.
So it's like having a robotic pilot on board?
In a way, yes. And the pilot can always take over if needed, and there's usually a dedicated button to disengage the autopilot.
Good to know. Now let's talk about environmental systems, things like heating and cooling the cabin.
Right. For cooling, you have options like ram air, which is basically just letting outside air flow through, and air conditioning systems, which are more effective but heavier and use more power. And in some cases, you can even fly with the doors off for maximum ventilation.
Flying with the doors off, that sounds a bit wild.
It can be fun, but you got to make sure everything's secure and the doors are stored properly so they don't get damaged. And for heating, piston engine helicopters often use a heat exchanger around the exhaust manifold to warm up outside air. Turbine engines typically use bleed air from the compressor mixed with ambient air to adjust the temperature.
Okay, makes sense. And finally, we need to talk about anti-icing and de-icing systems, which are essential for flying in cold weather.
Absolutely crucial. Anti-icing systems are all about preventing ice from forming in the first place. Turbine engines usually have an engine anti-ice system that uses hot bleed air to keep the inlet clear. And some helicopters have anti-ice systems for the airframe, like heated leading edges on the rotor blades.
And de-icing is about removing ice that's already formed.
Exactly. If there's any frost, snow, or ice on the helicopter, you got to get it off before you fly. It can really mess with the aerodynamics, especially on the rotor blades. And it's important to be careful about shedding ice in flight. It can damage the helicopter or pose a hazard to things on the ground.
So thorough pre-flight checks are essential.
Absolutely.
Yeah.
And if you encounter icing conditions in flight, you need to activate any in-flight de-icing systems you have right away.
Wow, that's a lot of information. We've covered everything from the basic structure to the complex systems that keep it all running. It's amazing how much goes into making a helicopter fly.
It is. And it's a testament to the ingenuity of the engineers who designed these machines.
And our goal today was to give you, the listener, a solid understanding of how these things work without getting bogged down in the technical details. Hopefully, we've sparked your curiosity and maybe even inspired you to learn more about these amazing flying machines. So, as you go about your day, think about this. How do all these interconnected systems, many with built in redundancy, contribute to the incredible safety and versatility of helicopters? And what new innovations do you think we'll see in the future that will push the boundaries of what these machines can do? Thanks for joining us on this deep dive.